Good evening. Can you hear me? Okay, thank you for your response. Okay, so today we will discuss seventh assignment. Here are 25 questions. Okay, so let's come to the first question. You have given electron mobility equal to mu equal to 1500 centimeter square per volt per second. Find the diffusivity at 300 Kelvin. These are the options. You have to find the diffusivity D. Do you know Einstein coefficient? Sorry, Einstein relation. Apply this relation d by mu kt by e. From here you can calculate mu kt by e. You have to find d. You have given mu and kt by e 0.26 electron volts, so this is in volt. At 300 Kelvin equal to 300. Now please try to solve this question and check your answer with options. Okay, A is correct answer. Okay, so see the solution. Clear, this type question may be asked in exam, so please ready with this type question. Let's come for next question. You have given tau. You have to find the diffusion length. These are the options. Yes, please try to solve this question. Diffusion length, how can you calculate? Do you know formula? Okay, L equal to under root D into tau. This is the formula. Please try now. Okay, D. So see the solution. D is given to you. What is D? D is 30 centimeter square per second, and tau is also given to you 2 microsecond. So first you have to convert this micro, 10 to the power minus 6 in second. Now put diffusion length under root diffusivity with tau. So diffusivity is 30, which is centimeter square per second. So, and this is in second, so your length will be in centimeter. Be clear about the, check the your dimension. So this will be around 7.75 10 to the power minus 3. This will be in centimeter because this multiply second cancel out, and centimeter square inside will be come into centimeter. Okay. So next question, which mechanism reduce carrier mobility in semiconductor? You have following options: phonon scattering, ionized impurity, scattering, increase relaxation time, defects in crystal. Which mechanism reduce carrier mobility in semiconductor? Mu. Do you know formula as we discuss? D by mu kt by E. This is Einstein relation, or you can rewrite like that, kt by, this is mobility, inversely proportional to the temperature, or temperature has two terms, minus 3 by 2 and 3 by 2. These are two scattering different. So temperature dependent, diffusivity, and scattering also, and diffusion length. T by 2. Tau also we can also correlate with tau, replacing this equation. So which is also so mobility, basically these are the material quality, tells about the material quality, so which is related to defects basically. So defects in crystal, ionization impurity, which is also defects, phonon scattering, which is also material quality, tells you, which is also related to the defects. So all these three factors, basically defects in the material, reduce the carrier movability of the semiconductor. If we increase the relaxation time, what happened with the movability? Can you correlate from here to? Increase this tau. Please convert this L square by d tau and calculate here L square by tau replaced by d. So movability from here, this equation and this equation with equal to d. What? L square by tau E by kt. So when we increase the relaxation time, this is increased movability will reduce. So also, but carrier diffusion length also play in the picture, so we can directly compare, we can't compare directly. So defects only we will assume the defects, or when we calculate by the experimental, you will get the component which is dependent, which is basically the defects. So please remember these defects. Let's come with next question. You have given tau is a 0.05 picosecond and effective mass electron is given also. Find the mean free path at room temperature 300 Kelvin. You have these option for following option: 1, 2, 12, 6.3 nanometer. You have picosecond and effective mass m naught is the electron mass kg per. You have to find the mean free path at room temperature. L VTH into 2. This is the formula you have to apply. How can you apply? So first you need to VTH. How can you calculate this? Any idea? Any idea? Mean free path of gases. For electron is like free electron. You have to apply free electron theory. Any idea? No. So let's see. Wait 1 minute. This is you have given effective mass. So from kinetic theory of gases you can calculate 3 kT by m effective mass. So from here, if you put kT by m you will get effective mass like that, and from effective mass tau is given. So mean free path you know distance, velocity and relation. So mean free path equal to VTH, which is related to the lambda, noted by lambda, into the relaxation time. So first you have to need calculate VTH. So he is already given to you, which is this 0.05 picosecond. Picosecond, how much picosecond? 10 to the power minus 12 pico in unit. Check your answer. Please calculate yourself and let me know this is correct or not. Yes, please do yourself. Are you getting? So how you know where is the KT by M? This is actually, you know, the three dimension. We have to apply X, Y and Z. Every direction has half KT. Along the energy stored, every direction has more half KT energy. So you have three dimension, which is multiplied by 3. So generally people like 3 KT by 2 with effective mass, or so this is come from to there 3 KT by effective mass, let's say come, and which is we will get the 1.25 10 to the power minus 10 to the power 5 as you calculated. So and so clear this solution to you. If clear, then let's move for next question. Which of the following statement are correct? This is the next question, and let's read the options. A single crystal silicon generally has the highest carrier mobility. Polycrystalline silicon has lower mobility due to the grain boundaries scattering, and amorphous silicon shows hopping transport instead of band transport. D. Carrier mobility in amorphous silicon is higher than in the crystalline silicon. Yes, please. You know the mobility is directly related to the defects as we discuss. Grain boundary. So this is the clue for this question. Now think and choose the options. As we discussed in the first question, movability related thing which is defects cause the reduction in the movability. Okay, A, B and D. Other, please try to give your response. Other members, please try to respond your options. Clue is that if has defects, more defects, less movability. Carrier movability will have less carrier mobility. Okay. Yes, please. So from this, let me give more. Single crystal is highest, then polycrystalline, then amorphous. These are the options. This will be the order of the movability because single crystal has lowest defects, then polycrystalline, then amorphous is highest. So, and one more the phenomena, amorphous silicon shows hopping transport instead the band transport. This is new mechanism in the amorphous. And carrier mobility in the amorphous silicon is higher than the crystalline silicon. No, crystalline silicon, whatever the polycrystalline or single crystalline, always will high. So that's why this is not will be the correct. Clear now? Single crystal has the highest. Polycrystalline has a lower mobility due to the grain boundary scattering, lower as compared to this, but more than the amorphous. Silicon has shows the hopping transport. In this, carrier move by hopping between the localized states. And other also 1 minute. This is about the movability also. Please read. In solid state physics, electron mobility characterizes how quickly an electron can move through a metal or semiconductor when pulled by the electric field. There is an analogous quantity for the whole called whole mobility, and term carrier mobility refers to general both electron and hole mobility. Electron and hole mobility are a special case of the electron mobility of charged particle fluid under the electric field. When the electric field is applied across the piece of material, the electron responds by moving with the average velocity called is drift velocity Vd. Then electron mobility is mu is defined as Vd equal to mu into E electric field applied. And how we can experimentally how we can determine this via Hall effect. Semiconductor will depend on impurity, concentration, impurity and concentration, including both donor and acceptor, defects, concentration, temperature, electron and hole concentration. It is also depend on the electric field, particularly at high field. When the velocity saturates occur, it can be determined by the Hall effect. Transistor behavior. So, if question asked in the exam like that, how you can calculate, how you can determine by experimental movability? Option are given, Hall effect and others. So you have to choose Hall effects. Clear? For the semiconductors. Okay, thank you for your attention. Let's come with next question. This is your next question. The starting material in the manufacturing of semiconductor grade silicon is silicon vapor, silicon tetrachloride, silicon melt, trichlorosilane, siloxane. These are the options. Grade silicon. D. Okay. Yes, please, other. So option trichlorosilane. Please see, this is picture taken from the lectures. Cement process trichlorosilane is the starting material. On we have to heat around 1100 degrees Celsius on heated silicon rod. So it will convert in SiCl4 and then to silicon Si, silicon grade, semiconductor grade silicon, and this is the reaction. So starting material, you have to Be focused, please. Okay, and please learn also the reactions, involved reaction in the process. In the Siemens press, which is the most common method for the manufacturing semiconductor silicon grade, starting with the trichlorosilane, which is SiHCl3, and trichlorosilane obtained from the metallurgy grade silicon through a reaction with the hydrochloric acid HCl, and the process involves the chemical vapor deposition CVD, where the trichlorosilane is decomposed on the heated silicon rod to produce high purity polycrystalline silicon. Yes, please see the next question. Which reaction occur during the silicon purification? How for purification, formation of trichlorosilane from the silicon and HCl, decomposition of trichlorosilane to silicon, reduction of the SiO2, the carbon hydrogen passivation of silicon. Yes, please. Okay, A and B. Okay, so reaction involve formation of the trichlorosilane from the silicon and HCl. Formation of the trichloro from the silicon and HCl. Purification involve decomposition of trichlorosilane to silicon. This is job, and reduction of SiO2 with the carbon. And hydrogen precipitation occur later in the solar cell fabrication. We have to, if we made the silicon solar cell, we will remove the surface dandling bond and effects with the passivation. So this is not the purification of the silicon part. This is related to the silicon solar cell. So as you can see the reaction like that here, also see the all the reaction available in your course. How you can purify HCl is also involved. Okay. Which statement about the silicon purity is correct? This is your next question. Metallurgical silicon has 98 to 99 purity. Semiconductor silicon has purity above 99.999, 4 times 9%. Solar grade silicon required purification. Silicon vapor are cut directly from the quartz. Okay, A, B, and C. Other, please try to recall you from the lecture if you have attended. And so this is your correct answer, A, B, and C. And dy is not correct because quartz is first reduced to metallurgical grade. We can't cut directly from the wafer to cut directly quartz. So first quartz is reduced to metallurgical silicon grades. Ninth question, which method are used to grow single crystal silicon wafer? Czochralski process, float zone process, cement deposition, molecular beam epitaxy for single crystal silicon vapor. B, okay. Multiple option may be correct. Please pay attention. Okay, so correct answer will be only A and B. Float zone is correct, but also Czochralski process. Grow bulk crystal cement process is for polycrystalline rod, not wafer. And MV is alag technique, which is not grow the single crystal of silicon. So please read about these process, how what is the starting material, what are the ending product, what are the purity, which type of crystal silicon are produced by this process. So be ready with these preparation for exam. Which of the following is are correct sequence of manufacturing of single crystal silicon? These are the options. Correct sequence for manufacturing of single crystal. Where did you start? From semiconductor silicon, then melting, solidification, melting grade silicon, purification, single crystal, or metallurgical grade silicon, semiconductor grade silicon, melting and solidification, purification, single crystal. Okay. So answer will be the C, metallurgical grade. This is the significant. sequence. Then we have to purify. Then semiconductor grade silicon we have to obtain, melting and solidifying, then single crystal will be obtained. So this process involved in float zone, you know, to make the single crystal. First, metallurgical grade silicon, which is hot as Mg Si production, obtained from quartz SiO2 reduction using carbon. Then purification, convert to Mg Si into the semiconductor grade silicon via chemical purification, cement process or flood design bed reaction. This is cutting, okay. Then melting and solidification. Then semiconductor grade silicon is melted and solidified using process like Chokrolsky and float zone method to grow single crystal. Single crystal silicon formation, a pure defects free crystal is obtained. That's why its cost is too high. Need lot of purification to make the single crystal. The process used to manufacture semiconductor silicon grade silicon is, yes please, these are the A, B, C and D options. Process name is given. So option cement process, union carbide process. Semiconductor grade silicon. Cement is also given to you, and other will be cement, union carbide is the cement is giving you to you 60%, and ethyl carbonation process also 15%, and union carbide process is 15%. Semiconductor grade silicon. Please see from this is picture taken from the lecture. Okay. This is the question. Okay, so we have to discuss this question. This is already solved, but let me give you how can we solve this like that question. Plot the doping distribution of the arsenic distance 30, 40, 50, 60, 70 and 80 centimeter from the seed in the silicon ingot 100 centimeter long that has been pulled from the melt with the initially doping concentration 10 to the power 17 centimeter. So you have to apply this formula. For the concentration we have to calculate. So already is given initial concentration which is C0 as is given to you 10 to the power 17. Such type question is too long, but you have to solve. And K naught is also given to you. The coefficient K naught for the arsenic is 0.30, and concentration at the point we have to calculate CS, which is represented by K naught C naught 1 minus L by L naught K to the minus 1. And now we have to calculate for 30, 40, 50, 60. So please calculate CS C naught K naught 1 my L by L naught K naught minus 1. You have C naught initially 10 to the power 17, K naught 0.3, and what else? L naught also you have 100 centimeter. This is per centimeter cubic. Okay. Now you have to calculate 30, 40, 50, 60, 70 and 80 centimeter. Please put the L value from here and now plot between the L by CS variation. Yes, please do. Let me calculate for you. First you try, please try. Yes, please do yourself. You can take 2 to 5 minutes for this question. Yes, you are correct for 30. Please calculate for the 40, 50, 60, 70 and plot the on the this plot length versus CS. Which type of curve will appear? Other, please try to solve. Let me calculate 480. This will be around 9 into 10 to the power 16. Yes, please give me the other. Okay, so according to you, 430 is 3.85, 3.85, then 5.5, then 6.2, and then 7.3, 8.9, and last 9.2 with 10 to the power 16 per centimeter cube. Okay, so these are the numbers. For 40, Okay, you are approximate. So these are the why is different. Just use the calculator and please check. You have to apply this formula, nothing more, and solve the. So like that. Okay, maybe the error, but like that you have to now 30, 40, 50, 60, 70, then on, and connect these point like that. So curve will be like that. Okay, so such type curve may be given and you have to choose the options in the curve. So please ready with this. You have to just check the one point for given, just this is correct or not, then you will get the answer. 1 or 2 points, just check 2 points. Last one, 90. If you land with the y-axis with the x for 2 value, you will definitely get correct curve. Not calculate the all, just check the 1 or 2 more. Wait. Okay, this is next question. Choklovsky melt is simultaneously doped with the boron to level 10 to the power 17 atom per centimeter, phosphorus to level of 18 10 to the power 16 atom per second. Does a p-n junction form during the growth? If so, what will be the fraction solidified? So you have to how to solve this type of question. Just you have to use this. Sorry, cannot see not 1 by L by L naught or M by M naught, and M by M naught will be the your fraction of solidification. You have to calculate this. Simultaneously boron level and phosphorus at the level. Boron and with phosphorus. Does this is make the PN? Yes, one has N type, other has P type. So this will be at the junction, PN junction will form. If we dope the P type and N type material with silicon, always make PN junction. Okay. Wait. So see the solution, please. I am noting here CS for phosphorus, CS for boron. Only PN junction if formed, then concentration will be the same at the PN junction. This is the key point, key message. So this is the trick for this question. So you have to apply now CS to close this is equation as we have already applied. This is solidification. K naught C naught 1 minus m by m naught, or you can get let L by L naught or m by n naught. K naught minus 1. Phosphorus you have given, boron you have given also along with the K naught. So this is, let me with the phosphorus, this is 8 into 10 to the power 16, and K naught 0.35, and for boron, this is for boron, this is for phosphorus. Okay, at the any point let me consider P and N junction. At this point, one side is P type, one side is N type. Apply this concept both side, and you have to calculate m by m naught. Just wait. Please see this solution and give me the answer m by m naught. You can take 2 minutes for this. Please see the solution and try to copy this and let me know you are getting or not. Yes, please do. Yes, please. this power with 18, this number cancel out, and will do the same. -1 also cancel out the same power. And what else? Just 0.35 equal to 1 minus m by m naught. Point 0.8 minus 0.35. And from here this number is 0.45. We have to take one minus m by m naught. You will 0.35 to the power 1 by 45, and m by m naught we will get 0.902 around. Okay, yes, you are correct. So please be ready such type of question if asked. Clear to everyone? Maybe ask such type, does this is p-n junction formation, or maybe such type, not long but just yes or no. Okay, so let's move on. This is the solution I did. See the next question. Which of the following belong to the first generation solar cell technology? Single crystal, polycrystalline, amorphous, or cadmium telluride? Yes, please. First generation solar cell. Okay, ABC. So first generation is vapor based crystalline silicon. Okay, this is your first generation solar cell, which is only vapor based. Amorphous is getting later on the second generation. Okay, so this is next question about second generation thin film solar cell, please. Yes, please. Next 15 question. Please try to give me answer. Amorphous, cadmium telluride, CIGS, monocrystalline silicon. So yes, you are correct. ABC is the answer. Second generation solar cell is thin film deposition technology. Correct. First is vapor based, second is thin film, and now is point for the third generation. Question is now for third generation. A, B, and C. A, B, and C. Okay, your answer is correct. DSCC, organic photovoltaic perovskite also. This is not the case. So third generation is M to exceed XQ limit, Shockley-Queisser limit to reduce the cost dramatically. What is the Shockley-Queisser limit? Shockley. What will be the efficiency according to the SQ limit highest? Anyone please? You have band gap easy versus like that curve, you have highest efficiency. Which is around 1.34. No, this is not the case. For single junction only, I am asking for only single junction, not multi junction tandem, like not. This is the band gap. According to the band gap, around 33%. around. We will get the maximum efficiency for single junction solar cell only 33%, which is band gap around material has band gap 1.34. Other we can't get like 80, 90, 100 because material will convert only efficiently only the this much amount when energy only. If cell light has energy, photon has 1.35 ev and more will convert, but more energy go will efficiently convert into the electricity because higher energy will give to you material heating and other phenomena. Only that much energy is required or something little more to give. So according to this band gap, you have maximum number of photons in the solar spectrum. You know, solar spectrum. Wait. Like that is spectrum. So according to this band gap, here is the maximum photon. So this photon will convert, give you highest efficiency. Okay. Other mechanism is that you have to use multi 1 2 3 4 like that material step by step, maximum then minimum then minimum then minimum. We will utilize first is maximum, then remaining will second, then third, then fourth, then we get around 80-70% for maximum. So but this process is highly costable, cost will be very high. We have to stack multi junction cells 1/1, so it will take huge cost and huge technology, advanced technology. Okay. Next question. Which statement about the solar cell generation are correct? Now please give me the, we have discussed first, second and third generation. Now this is question to you. First generation solar cells use thick vapor. Second generation solar cell reduce material uses. Third generation aim to improve efficiency beyond the traditional limits. Third generation cell always use silicon. Multiple option may be correct. And let me give to you single crystal thickness is needed 150 to 200 micrometer. Polycrystalline is needed around same, and amorphous is 1 micrometer. So second generation, this is, as we discuss, you know, second generation is also the amorphous. First is, so this is categorized in first. This is thickness is too high. So M2, the for second generation is, we have to reduce this thickness. Also the material uses, use thick vapor, and we have to reduce this thick vapor with optimum material. If material is less, cost will be automatically less. So second generation, reduce the material uses, and third generation is also M to improve the efficiency beyond the SQ limit. Clear? Next question, which of the following statement are correct? #18 question, please see similar type question. Yes, please, 18 question. B and C. Also A is also correct. First generation solar cells generally have high efficiency but the higher material cost. As you know, single crystal has higher efficiency. Single crystal silicon solar cell has highest, which is categorized in the first generation. Crystalline silicon, higher efficiency. Second generation is reduce the cost by using thin film, and third generation technology aim to improve efficiency. And third generation solar cell already dominating. No, this is not dominating. Silicon only dominating. Which of the following belong to a family of chalcogenide? Next question. Cadmium sulfide, gallium arsenide, amorphous silicon, cadmium telluride, polycrystalline silicon. Okay, yes, please. So, chalcogenide is the family of sulfide and telluride. Chemical compound consists of at least one chalcogenide anion, at least one more electropositive element, although the group 16 of the periodic table chalcogenide. Intermediate chalcogenide are more commonly reversible sulfide, selenide, telluride, polonite, and oxide rather than the oxide. This is the next question. Which of the following is are commonly impurity element in the material grade silicon? Tin, aluminum, zinc, calcium, lanthanum. B and D. Okay. So aluminum and selenium, calcium, sorry, not selenium, openly found to the metallurgical grade silicon reduce the impurity. So these are the this is the explanation, please see. Also production of the metallurgical grade, you can see SiO2, then to carbon, silicon, carbon oxide gas is will evaporate, and also the process you can see below. This is the temperature. Liquid silicon you will get purity, then impurity Fe, this is the impurity. Aluminum, it is 0.4 to 0.7%, and this is 0.2 to 0.6%. Okay, so this is the highest impurity you will get. Next question. In the gallium arsenide, dopant typically produce n-type conductivity. Zinc, selenide, selenium, carbon, beryllium. Twenty-one question. So answer will be the B, selenium. N type you can see Si, Si, Sn, G site. P type As site you have to doping for P type and N type. So please remember these also. Clear? Let's move for next question. The intermixing of cadmium sulfide and cadmium telluride layer in the cadmium telluride solar cell leads to. So this is basically answer, decrease in the quantum efficiency. Why? Let's see the solution. Explanation. The intermixing of cadmium sulfide cadmium telluride in the cadmium telluride solar cell leads to the transformation of this alloy cadmium 1 cadmium sulfide X tellurium 1 minus X alloy at the interfaces. This alloy has a higher band gap than the cadmium telluride and can impact the quantum efficiency of the solar cell, particularly shorter wavelength. Cadmium sulfide band gap nearly 2.42 eV, while that has the 1.45 cadmium telluride. Mixing which absorb fewer lower wavelength, higher photons. So if the band gap is increasing, one minute. So as you know, band gap is increasing, your quantum efficiency will decreasing, because let's say you are in this region, So this is Q the highest, then as we increasing the band gap, this is higher energy, this is band gap increasing this side, okay, and the beyond the band gap efficiency will 0, quantum efficiency. So your material, if say has a that much band gap, so your efficiency now will reduce. Earlier is that much, that area. So when the intermixing occur, it creates region with the higher band gap with calorimeter which absorb fewer lower wavelength, higher energy photons. Only this fewer wavelength, higher energy. Let's say this domain talking about. Result in decreasing quantum efficiency at lower wavelength. Blue side, this is called blue response spectrum. So band gap is reduces and your automatically quantum efficiency will reduce. Next question, reduction in the thickness of the cadmium sulfide window layer in the cadmium telluride solar cell mainly leads to increase in quantum efficiency, decrease at longer or shorter wavelength, increase in the recombination, reduction in the band gap. Yes, please. Okay, so your answer will be correct. Increase, if we reduce the thickness, automatic window layer which is not allow the more photons, if we reduce the window layer and which is higher band gap, so this is barrier for the higher thickness, but we let me remove the thickness, more photon will allow this window layer, so efficiency automatically increasing at shorter wavelength side. Which of the following can be used to window layer in a gallium arsenide solar cell? Sorry, this is your question. Network may be slow due to this. Okay, so indium galvanide arsenide or aluminum gallium arsenide, as we discussed earlier, can be used to window layer. In gallium arsenide solar cell, window layer material that allow the light to pass through the minimizing carrier recombination and the absorb minimum photon to its cell. Choice should be have wide band gap to reduce the absorption and enhance the transparent good lattice matching with the gallium arsenide defects and improve the efficiency. These are the criteria for choosing. So indium and aluminum band gap can be tuned by doping this and used as a window layer. Okay, so this is your last question. Which process improve the performance of cadmium thin solar cell? Cadmium cell to treatment, grain growth annealing, increasing interface defects, surface speciation. Yes, please. So cadmium chloride treatment, also grain growth annealing, and also the surface patient increasing the interface defects. This will reduce the performance. Okay, so this is all about today lecture. Thanks for your kind attention. If you have any question, you can ask me. If not, then let's meet for next Monday. We will meet again on next Monday. Any doubt? I'm not your ticket whole tickets. You can ask directly via the organized team. I'm not aware of this. IIT Madras will give you response regarding this. You are getting very soon, I think. This is last week. Again, next week will be the last. Next will you will get in the next week, I think so. Okay, so let's meet with the next Monday. Then after that I will revise 1 to 8 lecture, all assignment and your doubts in the last session after Monday, Tuesday, I think. Tuesday you will get the email regarding this. Okay, so let's thank you. See you soon on next Monday.